right.
Should we talk about at rest first?
No. How about instead of going through all of them, they're the same, we just say the difference first.
Okay.
Will and Mins has the person for at rest.
Oh yeah.
Oh, is that?
No, that wasn't in purpose.
Okay.
Oh, okay.
Well, that could make sense if there's like if it's just like holding onto the box, he's just not moving.
But that wouldn't be a force.
Yeah, that
There would be no force on it. So there's no interaction.
Yeah, it would just be force of contact.
I agree.
But the
That would still be a
difference.
contact force, right? He's just saying.
Yeah.
He's just touching it.
No. If he's touching it, no.
So just like the force. Yeah, the force is just like not
That's preventing it from going down.
Yeah, but that's preventing it.
Going down.
I think we're assuming that at rest, the person is not touching the box.
Yeah.
So,
Okay.
contact. So what do people say their difference was?
The difference was pretty much that since there was no rubber on the bottom of the box, there was less friction. Therefore, the person had to use less force to move the box.
Yeah.
And to reach that constant velocity.
Yeah. Because it's the same constant velocity, so there was less shear force going in the opposite direction, so therefore the person pushed less.
One thing that I see that's difference among all of our graphs is the FN, FF, FC, FP.
Yeah.
We just go around. I can't really read all. Can we? Can each person say what they did?
I thought we weren't going to use FC anymore.
Mm-hmm.
So I don't know if anybody else has some FCs. I think I see a few FCs.
That's okay. I mean, I guess yeah, it is better to probably say FF versus FN because to distinguish between friction versus shearing, it'd probably be better if we not say FC because
Isn't friction shearing?
Yeah.
Yeah.
that's what I'm saying.
Okay, so then just a question on your graph, because so you have Fn pointing that way for force natural, correct?
Normal.
Or normal, sorry, force normal.
Which are you talking about? The
Constant
last
velocity, the last one, and then you have force of friction pointing as if you're pushing the box that way.
One? Yeah, we should be the other way around.
Should it be?
Which way are we pushing the box?
Yeah, I guess I mean as long as it's
They never
As long as
specified.
the opposite, then it, yeah.
yeah, I mean I guess
Okay.
yeah, it's probably okay.
I'm curious about how people show the difference in the diagrams. I found it personally pretty difficult. So,
We just kind of drew shorter arrows
Small
left and
lines.
right because it's less force. I think similarly as we were talking about like what was it called, motion diagrams, motion maps. Those arrows represent velocity. I feel like in some sense with these free body diagrams, the arrows represent force.
yeah. We kind of just labeled it to be half of that, the previous one, because my aerodrome skills are not that good.
Well, do you know it's exactly?
Yeah, what do you guys have?
I just got half because I said it was going to be less.
Well,
So I didn't mean it to be half, I just meant it to be smaller.
alright, so it's not, because we don't know if it's like exactly half friction.
We don't know what the starting value is at all either.
Yeah, we're just kind of assuming, playing with context.
Do we have this, or do we want to keep talking?
I think
we have it pretty much now.
Okay. I want to ask you two quick questions just to kind of follow. Why are there two normal forces in your drawing, Will?
So I think you're talking about the last one.
Yep.
Yeah. I guess we have the upward force of normal, which would be the ground, the floor has a normal force, right, going up. And then there's the frictional going the other way. And then there's the
pushing.
It's
the
like
pushing is the other one, right?
Wouldn't that not be a normal force though?
Yeah, well,
Pushing is
pushing,
a normal force.
the friction is the shearing, but the pushing is perpendicular.
So it's the person who is doing a normal force, and then the floor wouldn't they be doing a
If the
force of
side of the
friction?
box
Oh,
is
they would do
plane,
both.
The
Because it's
person
going
goes
against
like
gravity and
this,
towing
and the
it.
floor goes like this.
So there would be two directions with the floor.
if the floor is the plane, then the normal force is going like that, so it's perpendicular. But if the side of the box is the plane, he's pushing that way, so
It's
the force is going that way, so it's also perpendicular.
So I'm going to ask a question that may or may not add a lot of time to this discussion. If the force of gravity isn't a natural force, and it's pushing, then what is it if it's pulling?
So the gravitational force is not a contact force. I'll just step in for
Right.
this for a minute. So it's kind of separate, and we don't kind of want to consider whether it's normal or frictional, because it's not. We only classify contact forces as normal and frictional. And natural is a word you said twice that we don't use, but is a really common term that comes up when we're putting the
I
thing.
keep on saying natural, normal.
Yeah, that's
Normal,
okay.
Normal.
Okay, are we clear on that? Do we feel it's okay to have normal forces that point to the side? And we understand what we're saying. What would help for clarity's sake in kind of doing that? You know, I notice like we have different conventions we're building about how we're labeling our forces. Like in Lenny's diagram over there, I feel like, you know, their diagram looks different than Will's diagram in terms of the information they're passing on.
I guess friction should be FS for, for shearing.
Oh, I think it's okay to leave friction as friction. Like we in our mind know friction and shearing are the same thing. Shearing is what we see. You know, like that's how we envision it. But one thing that's missing from Will and Men's diagram that might clear things up would be what?
What's applying the force to where?
Yeah. If you could identify the objects that are exerting the forces, that can be helpful. You don't have to do that change now. So last thought that I want to have you think about, maybe only for 2 more minutes, is you said in the beginning that you didn't want the hand touching the box. But as you can see, my hand is touching this box right now, and it can exert a force on it, right? We would agree that my hand is exerting force. It's even a normal force, right? Because my atoms in my hand are crunched and atoms in the box are crunched. And yet,
The net force is still 0.
The friction is greater than the force
Yeah.
you're applying to the box, so it's not.
Yeah, the net force here, that is constant velocity.
Because you're trying to make it shear. You're pushing it in a way that would cause the box to shear if it were to move. And that amount of shearing is too much for you to move it at that amount of force.
If you have a big boulder and it doesn't move, it doesn't mean that you're not putting force on it. It just means that there's too much mass or friction effect, so they can't move.
am I doing a good job of not giving you any indication whether you're right or you're wrong?
Yes.
Yes.
Awesome. I win.
This may or may not be right, but you need a net force of 0 in order to attain constant velocity, which may not be applicable when you accelerate, but same concept may apply of having to have a greater contact force in order to overcome the friction force. Am I basically saying what other people just said?
Yes.
Okay.
Let me ask one question. What is the net force on the box right now?
0.
Nobody wants to argue with me on that?
Well,
No.
well, well,
It's
no.
0.
It has a constant
Zero.
velocity.
It has a
Zero.
constant velocity because friction's going one way.
But
Works
if he
hand.
takes off his hand, it's 0.
As
And
well.
but he's adding more.
What's the net force right now?
0.
Zero.
Now he's
Zero.
adding.
It's because there's friction now. There's friction going on right now.
Yeah, that cancels out the push.
There's no friction. It's
Yeah.
That's what's not allowed to move, because if there was no friction.
It was too small. Okay, the value of the
Comparison,
force
yeah,
added
yeah.
on there would be so minutely small that it wouldn't even matter.
Well, it's kind of like what we drew here. So when Mr. Burke's hand is not on it, it's just upward and downward forces. But when his hand is pushing, it's exactly.
There's 2 more forces.
In fact,
Okay,
even if
but
the
that
box were to
is
move.
so small.
Yeah, but there's
That is
No, but
so
you
small.
still there's still force. You still have to draw it,
A little bit of force.
and then that
Daniel,
force
come
is
here.
0. So.
I'm gonna push Daniel the same way I'm pushing the box. Tell me, is this force small?
What are kind of
Kind of. I mean, is it too small for you to matter to you?
no.
Right. Do you want me to keep doing this all day? No.
It's still a force, like, but what's going on is it's.
It's not enough to displace it.
In fact, even if so, what would happen is what's happening even when the box is moving at a constant velocity is that same exact thing. The force is the net force is 0, so the box continues to move at a constant velocity of whatever the box was moving at. Here, the box is moving at 0 centimeters per second. It's moving at 0. It doesn't have a its velocity is 0 because the net force is equal to 0.
Isn't the net force not equal to 0? Because in order for the box to move, the person pushing it needs to be putting more force on it than it's.
I'm saying when he's pushing it and the box is
Ooh,
not.
I'm going to pause and I want to bring Eleni's ideas back because it's such a good idea. And I want us to,
If it's-
you know,
if
and
it's-
I'm actually gonna put Harrison on pause for a little bit because I want to hear, you know, no offense, I just want to hear some other voices. So repeat everything that you said, because it was a really awesome moment, and I want for a minute for everyone to address their concerns to what Eleni just said.
If it's not moving, then the net force is 0 because you're not putting any force on it and it's not putting any back to you basically. But then in order for the box to move, you need to put more force on it than it's putting back to you. 'Cause if the
But
net
if it's
force-
sorry.
If the net force was 0, then it wouldn't be moving. The amount of force it'd be putting on you would be the same as it's putting back.
But if it's at a constant velocity, the net force can be 0.
Yeah.
Well,
Yeah, but she's talking about speeding up.
I think we're
Okay.
talking about like
She's
acceleration.
talking about changing
and how-
velocity.
Yeah, it's like when you have enzymes in biology or whatnot, you need a certain amount of activation energy in order to start the process. Does that make any sense?
Are we sufficiently confused right now? Is there good confusion?
Yeah.
Can we move on and try number 3 and come back to this?
Yes.
Okay, so you don't have the full picture here right now. Like you've got these boards can be right, and yet you don't have this perfect, right? And there's even little mistakes that are kind of coming up in the way that you're talking sometimes about the other stuff that you want to be attuned to. So I'll make it a little easier.